In this video, we'll use the Mighty Data Channel modifier to create an eye-popping animation of a grid of moving blocks. Before we get started, however, download and open the sample scene provided in the description section of this tutorial. The scene contains a helper object constrained to a path, which provides the motion for the animation. Our camera's look-at target has been point constrained to this helper, while its position has been manually keyed. To optimize performance, we've created two grids at different resolutions. We'll be using the lower resolution grid as we build our operator stack. Once we're happy with the results, we'll instance our creation onto the high resolution grid. Note that both grids have a planar UV mapping. This is an important detail in order to correctly color each cell with a bitmap. For rendering purposes, we've assigned a white background color to the environment and a default physical material to both grids. Our first order of business is to add a bit of noise to animate each grid cell. To do that, a first reflex might be to use the noise modifier. However, this would distort the grid's blocky look. So instead, we'll use the data channel modifier, which can add the noise without this unwanted effect. First, let's add a distort operator and use a noise map to drive the distortion. Press M to open the material editor and drag the noise map over as an instance. Using fractal mode with 8 levels gives a great result for this animation. With auto key on, we'll now animate the phase across the timeline. We'll remove the easing of the phase's keys by converting the segment to linear. Now it's time to add GeoQuantize to our stack. This sci-fi sounding operator simply takes the values of all the vertices that belong to a given element and averages them out. The averaged result is then reassigned back to the vertices. As you can see, the averaged noise produces a kind of blocky look, which is what we want for the animation. We'll now close this flow off with the vertex output. Here, we're adding the noise data to the Z position of each vertex. The effect might be too subtle to notice for the moment, but we can fix that by increasing the strength on the distort operator. Now that we've taken care of the grid's background noise, we can really start making the animation visually interesting. Our goal here is to scale each cell based on the helper's distance. To do that, we'll start a new data flow within the same operator stack. Add a node influence input. Now, you might have noticed that the operator appeared with a different icon this time instead of the usual input arrow. By default, if you already have one input operator in the stack, any further ones will appear in the multiply blending mode. This mode lets you blend a variety of inputs together, which we'll get to in a bit. But for now, we'll right-click to revert the node influence to replace mode and drag it above the distort operator. Pick the path-constrained helper and make sure the influence is set to by element. When we scrub the timeline, we can now see the influence as it moves across each element. Next, we'll add a transform elements operator, which we'll also set to replace mode. Transform elements is a bit of a special operator and should always be set to replace mode regardless of its position in the stack. Other input operators, however, are more flexible when it comes to blending modes. Use a vertex output operator to close this data flow out. Here, the position of each vertex is replaced by the data flowing out of transform elements. Another point to keep in mind is to make sure the input channel is set to from stack so it can operate on the incoming node influence. Note that transform elements also always needs some form of input, be it from the current operator stack, from a soft selection, or from something else. If you notice it's not doing anything, it's likely because it's reading from an invalid input channel, or because you're missing a selection in the stack. Back in the node influence, we can use the hold time to stretch the effect across multiple frames. Setting it to 300 will cause the influence to persist over the whole range of the animation. We can also modify the strength and the radius to avoid any tapering effects over time. To complete this part of the animation, we'll key the expansion of the radius to control the filling effect. We now have two data flows in the same operator stack, but why stop there? Let's add another one to color each element based on a bitmap. Add the color elements input to the stack. As you can see from the icon, the color elements operator works with faces. However, our stack only has vertex data currently flowing through it. In this case, we'll need to switch modes to replace the current data flow. The idea here is to color each element and to store the values in the vertex color channel. Since we know we want to end up with a vertex color, we'll add a vertex output to close the data flow off. It seems our data types are now mismatched. Color elements is working with face data, but vertex color needs vertex data. To fix this, we can simply add a convert to subobject type operator. Everything's working again. In the color elements operator, we'll go ahead and set the map channel to 1 to sample the map in the geometry's UV space, then enable Use Element Center, and then set the dropdown to Element. Next, set the map to use the logo bitmap. If the blue vectors you see here incorrectly display for this operator, you can just ignore them. Since we're stuffing this data into the vertex color, we can pull it back out in the material graph. Connect a vertex color map to the base color map. When we hit render, we can see how the cells of our grid are now individually colored based on the bitmap. To complete the animation, we'll create a final flow of data that'll grow each cell based on color intensity. In particular, we want the 3 to stand out from the rest of the white cells, and to do that, we'll use another distort input. We'll reuse the same bitmap from the color elements operator. And we'll add another geoquantize to average out the distortion across each element. We now want to use this data to move each vertex along the Z component of its normal, so we'll add a vertex input in multiply mode. Close this flow out with a vertex output in position mode. The data in this flow will be added to the current Z position of each vertex. When we tune the strength on the distort input, however, we see that we're getting the reverse of what we're aiming for. The 3 stays recessed, while the rest of the cells extend upward. To change this, we'll need a curve to remap the data. Enable the Normalize checkbox to make sure the curve operates on the whole range of data. We'll remap lower values to higher ones and higher values to lower ones by reversing the curve's endpoints. We can now add one last node influence to focus the bulge closer to the 3 and to reduce the text extension in the lower right corner. To get a nice preview of our animation, select the following output operator. The final step is to copy the data channel modifier onto the high-resolution grid. Paste it as an instance. At this point, playback might slow down because of the number of operations performed on each vertex, but our final result is ready to view. We're now ready to sit back and hit render.